Hi, and welcome to According to Pete. It's the end of September. We are fresh back from Maker Faire and Open Source Hardware Summit. Good to see all you guys out there. It was a good time. Talked to a lot of people, heard about a lot of projects, got a lot of ideas, so we're going to start jumping on a lot of that stuff real soon. And today I'm going to talk to you about 555 timers. What's that, you say? Oh, come on. You all got to know what a 555 timer is, right? Right? No? Okay. Well, a 555 timer is a little dude that comes in a SOIC 8, not SOIC, a DIP 8 package. 555 is a single unit, 556 is a dual, 558 I think is a quad. It's a little timer circuit that you use some passives on, and it kind of gives you, it'll oscillate, it'll do PWM, it'll even work as an FM transmitter, not a transmitter, but it'll generate FM with its PWM function. It's a cool little part. It's been around since the 70s, and it's sort of become a mainstay of beginner electronics. So today I'm going to run you down a little block diagram of the insides of one, and then I'm going to give you a couple of examples of how to operate one in a couple of different ways. And at the end, I'm going to give you an example made from a kit made by a friend of mine that really annoys the heck out of most people around here. So this is the innards of a 555 timer, okay? At its heart, you have a basic flip-flop. I hope you know what a flip-flop is. If not, put a little note in the comments below and say, dude, talk about flip-flops. Roughly, set, reset, Q, Q naught, and the uber reset, and that's a global thing on the 555 part. But the flip-flop itself, when set is high, Q will also go high, and Q naught will go low. Crazy. When reset is high, Q will go low, and Q naught will go high. Now, also attached to this thing is this little AI out here, NPN transistor, and external to the part is a pin called discharge, and we'll get into what that's all about. Basically, it's used typically for discharging a capacitor that's in the circuit, which you may or may not be using. You probably will. Then there's an output pin that comes directly from the flip-flop, or it may have a driver on it, I don't know. Output capacity of this thing, it'll drive about 200 milliamps. Now feeding the flip-flop are two comparators, okay? And each comparator is set up on a threshold voltage. This voltage divider is, again, internal to the 555. And these three resistors are equal value. What value? I don't know what their values are. I wasn't able to find that in a data sheet, but I expect them to be somewhere in the neighborhood of, I don't know, 47K to maybe 500K at a guess. And each of these is set at a reference. This comparator is set at a reference of 1/3 VCC, so your supply voltage. And the supply voltage can be between 4.5 and 16 volts for the part that we sell. It's a TI part. You can find it in our catalog. And the upper comparator is set to a reference voltage of 2/3 VCC. Okay, simple enough? Now, there are two pins here. One is called trigger, one is called threshold. In general, when trigger is pulled low, lower than 1/3 VCC, it sets the output high. Okay? Output's high, discharge transistor is off. Okay? Threshold. When the threshold pin is taken higher than 2/3 VCC, this is all reset. Output goes low, discharge transistor turns on. Okay? Then there's this guy, the control pin. This is here so that you can actually muck with these reference voltages. I've not seen an example of anyone actually doing it, but there's a pin there. You can do it. So, you know, if you want to experiment with this, that'd be one place to go. So the external pins, let me make sure you understand this. VCC is an external pin. The control line is an external pin. Threshold and trigger are external. Ground, right? Here's ground here, here's ground here. It goes to one pin on the device. Discharge, output, reset, and reset is low active. The reset pin, if I didn't say this earlier, what it will do is it will interrupt any of the timing that's happening outside in the passives, and it will reset the circuit entirely. So now, let's get into the different configurations. This is a monostable configuration. Monostable. Now, the way this circuit works is that normally it sits in the low spot, right? The output will normally be at 0 volts. So in the 0 volt state, this discharge pin is active, right? So this guy has been discharged and this line is pulled low. It's pulled to 0 volts, okay? Now, what happens is that you pull the trigger pin low, and when you do that, the output goes high. Crazy. And when the output goes high, the discharge pin goes to a high Z configuration, so this becomes an open circuit. Now, C1 starts charging through R1, right? C1 will charge until it gets to the threshold voltage. You see that discharge and threshold are connected here, all right? So this line will go up to the threshold voltage. When it gets to the threshold voltage, the output will go low, okay? When the output goes low, discharge gets activated, C1 discharges straight to ground. This period T can be determined by these equations. So T equals natural log of 3 times R1 C1. Or you can approximate it as 1.1 times R1 C1, okay? Simple enough. Now when you set up this circuit, you're going to want to decouple the control line. You don't have to, but they recommend that you do. And they recommend that you use like 10 nanofarad or 0.01 microfarad. You want to pull your reset line high. It's a low active reset line, okay? And VCC and reset tied together, top of R1, so that's cool. Now, what you don't see here, I didn't put a decoupling cap on this, and somebody busted me a few episodes back. Why? Why, oh why didn't you use a decoupling cap? Please tell me. Look, man, if you've got a monolithic part, put a decoupling cap on it. From here on out, I am implying, if you've got a monolithic part like this, like a DIP 8 or SOIC or what have you, decouple it with like a 0.1 microfarad. Just good rule of thumb, all right? I might not put it in the diagram. It's there. It should always be there. So what this is good for is for PWM, right? You can set up your pulse width with these two components. Simple enough. It also works really well as a Schmitt trigger. So in case you need to filter noise out of another signal, good application. Sort of looks like a one-trick pony though, huh? Well, hang with me, okay? The next example is a little more interesting, and then the big kahuna is coming at the end. This configuration is called astable. Astable. It does not have a stable place. It's basically bouncing between ground and VCC. If you assume that the cap, and this is, you know, T equals 0, sort of like that, at the beginning of the thing, the cap is charging up. Trigger has been pulled lower than 1/3 VCC, so the output is low, okay? Now when the cap is charging up, it's charging through R1 and R2. Fair enough? Okay. Now when the voltage on the cap reaches 2/3 VCC, and you see here trigger and threshold are tied together, when the cap reaches 2/3 VCC, the output goes low, discharge pin becomes active, and the cap discharges just through R2. Again, like the other configuration, you want to tie or decouple your control line. Not mandatory, good idea though. Reset line is pulled high, VCC is there, output is going to look like a square-ish wave, but you can already see if you're charging through R1 and R2 one way and then discharging just through R2, this is not going to be a square wave. It's going to have a little bit different duty cycle than 50/50. So when you're calculating the frequency of this guy, F, right, 1 over the quantity, and if you count your parentheses, this is all one quantity, natural log of 2 times C1 times R1 plus R2, all right? That will give you your frequency out. Fair enough. Now, if you just want to calculate the time that it's high, it's this guy. Time high equals natural log of 2, right, times R1 plus R2, which is a quantity, times C1. Simple enough, right? The equation shows that your high time has these two components in the resistor portion and C1, obviously. Now when you want to calculate the low time, it's just R2. Time low equals natural log 2 times R2 C1. And there. So what? Well, hey man, it's an oscillator. That's that's pretty cool. You can make tones out of this thing, man. So, but still, it's sort of like, well, gosh, Pete, that's interesting and all. Well, okay, now we're going to get into the practical example. So, what can you do with all that junk I just showed you? This guy is an Atari Punk console kit. Okay, I got this as a demo from my friend Jimmy Rogers. Thank you, Jimmy. Props. What it is an astable configuration 555 timer followed by a monostable configuration of a 555 timer. And it's in a single package called the 556. I think I mentioned that at the very beginning. And so what you get is the frequency, right, and then a pulse width on top of that. And my kids totally love this thing. Why? Because it makes a ton of really annoying sound. Crazy stuff, man. Now, another thing that I figured out it's good for on Sunday morning with my wife is guess that song. The point is that with just a couple of things, you're able to put together a really annoying kit that I absolutely love. Thanks again, Jimmy, for this particular example of a 555 timer that I really, really dig. So that about wraps it up for today. Thanks for watching. Next episode, we may be back in my garage, depending on how much time I get to work on my stereo project. We could be working on the faders with the XB and the Arduino. Not sure. I might buy myself some time, though, and come back in here and address some of the other questions that are in the queue. Until next time, thanks again for watching. Keep the questions coming. You can put your question in the comments below, or you can send them to feedback@sparkfun.com with "according to Pete" in the subject line, and they will be put in the queue, and we will have a look, and we'll get them posted. So, thanks again. See you next time. Bye. Kill me! Oh God, kill me!